getting into something fundamental, quantum mechanics. Now, this theory is staggeringly successful. It underpins, well, almost everything modern. Semiconductors, lasers, nuclear energy.
The calculations are incredibly precise. We can predict outcomes with amazing accuracy.
Exactly. But here's the kicker, right? Ask physicists what it actually means about reality.
And you get a room full of arguments.
Yeah, it's this huge gap between the math working and us understanding what the math is telling us about the world.
That's the core of it. We have the mathematical formalism, the Schrödinger equation, the Born rule. These tools work, they're tested. But then there's the interpretation, the story we tell ourselves about what's really going on. What kind of reality does this math describe?
And that story is what we're exploring today. There's this novel idea, an oscillatory model for quantum reality. It's a different interpretation, a new story that maybe pushes back against some core quantum ideas.
It aims for something maybe more intuitive, perhaps.
Maybe. So let's dive in. Let's explore quantum interpretation and see what this oscillatory model is all about. Okay, so let's try and unpack this model. The proposal is that it's a deterministic model, an ontological.
Right. Ontological meaning it's trying to describe what reality is, objectively, independent of us looking.
And deterministic meaning no fundamental randomness.
Exactly. It suggests the probabilities we see in quantum experiments aren't the fundamental layer. They emerge from something deeper, from processes happening incredibly fast, way beyond what we can currently see. And these underlying processes are, well, deterministic.
Okay, so what are the key ideas here?
Well, first, this ontological determinism. It says every particle at every single moment has a definite, real physical state. Properties like position, momentum, they aren't fuzzy or undefined. They exist, but they're changing, fluctuating incredibly rapidly.
Constantly jittering,
Yeah,
sort of.
You could think of it that way, yeah. Second, the wave function, psi. It gets a pretty radical makeover. It's not the complete description of a single particle anymore. Instead, it's viewed as a mathematical handle on the infinite complexity of the universe.
Whoa, okay. Infinite complexity.
Yeah, suggesting a kind of deep interconnectedness, the whole universe influencing the parts, holism.
And how does that influence happen?
That's the third point, a proposed physical mechanism for non-local influence. This universal complexity isn't just an abstract idea. It's supposed to affect particles through actual reverberations in spacetime, like ripples in the fabric of the universe carrying energy and information.
Ripples in space-time. Okay. And this leads to superposition. How does that fit?
Right, this is a big one. Superposition in this view is a time-averaged effect. Forget particles being in many places at once. Instead, imagine a particle oscillating, moving through a whole range of definite states extremely quickly.
So fast we can't see the individual states.
Precisely. What we perceive macroscopically over time looks like superposition. It's the averaged out picture. And the timescale proposed is, well, it's mind-bogglingly fast. Approaching Planck time.
Planck time. That's 10 to the minus 44 seconds, roughly.
Something like that, almost inconceivably fast.
So this model is saying particles do have definite properties, always. We just see a blur because they change so fast.
That's the core idea, yes.
That feels more classical, in a way. It lines up with Einstein, Schrödinger, Bohm. They all wanted that observer-independent reality.
It absolutely resonates with that realist tradition, yes. Think of the EPR paradox, Einstein's argument that properties must be real even if unmeasured. This model provides a potential how.
And it's not just philosophy. It's proposing an actual physical process, these space-time reverberations. That's where it gets really interesting. Okay, but to really get why this is such a departure, we need to quickly touch on the standard view, right?
Yeah.
The Copenhagen interpretation.
Definitely. You need to understand the reigning paradigm to see what's being challenged. Copenhagen is, broadly speaking, the orthodox view.
So where does superposition come from in that picture?
Mathematically, it comes from the linearity of the Schrödinger equation. Basically, if state A is a solution and state B is a solution, then A plus B is also a valid solution. This means a quantum system can be described as a combination of multiple possibilities simultaneously, mathematically at least.
But that leads to problems, right? Like the measurement problem.
Exactly. The math works beautifully for tiny things, but if you scale it up, it predicts, say, a cat being alive and dead, or a pointer being up and down. We don't see that. That's the measurement problem.
And how do we get probabilities out of this fuzzy picture?
That's the Born rule. It's a crucial addition to the theory. It says you take the wave function, square its amplitude, and that gives you the probability of finding the particle somewhere.
It works, but we don't quite know why it works.
It's essentially postulated. It connects the math to experiments, but its deep origin is still debated. It's a fundamental rule we add on.
Okay, so Copenhagen's main ideas are,
Well, first, intrinsic indeterminism. Reality itself is fundamentally probabilistic, fuzzy, until a measurement happens. It's not just that we don't know, the properties aren't defined.
and measurement forces a choice.
That's the second and most debated idea, wave function collapse. Measurement is seen as a special, abrupt process that forces the system out of superposition into one single definite state.
The infamous collapse.
Mm-hmm.
Copenhagen's solution to the measurement problem, but it feels a bit ad hoc.
It does raise questions about what constitutes a measurement and how this collapse happens physically. The theory doesn't really describe the collapse mechanism itself.
Okay, what else?
Then there's complementarity, Bohr's idea, things like wave-particle duality. Quantum objects show contradictory faces, sometimes like a wave, sometimes like a particle, but never both at the exact same time. How you measure determines what you see.
And finally,
The Heisenberg cut. This sort of conceptual dividing line we draw between the quantum system we're studying and the big classical measuring device we're using. We need that classical anchor to get definite results.
so the big tension is that measurement problem. Schrodinger's equation predicts fuzziness, even for big things, but we see sharp reality. Copenhagen solves it with collapse.
And the oscillatory model solves it by saying the system was never fundamentally fuzzy, just oscillating really, really fast between definite states. Measurement just catches it at one point in its cycle.
A very different approach. It avoids collapse entirely.
Exactly.
So how does this oscillatory idea fit into the bigger picture of quantum interpretations? Where does it belong?
Good question. It fits squarely into the category of deterministic hidden variables theories.
Hidden variables. Like extra information we just don't have access to.
Precisely. The idea is that quantum probabilities aren't fundamental randomness, but arise from our ignorance of some underlying hidden properties. Like flipping a coin, it seems random, but if you knew the exact initial conditions, you could predict the outcome.
So in this oscillatory model, the hidden variable is
It's the particle's exact physical state, its precise position, momentum, whatever, at any given instant. It's hidden only because it's changing at that insane Planck scale frequency. We can't track it that fast.
Okay, and let's quickly revisit the mechanism. You mentioned this infinite complexity of the universe.
Yeah, that acts like a kind of universal information field determining particle behavior. It's conceptually a bit like the universal wave function in other holistic theories.
And the reverberations in space-time are how that information gets around.
That's the proposed physical conduit, yes. And this links up with some really interesting modern physics ideas. The zero-point field, vacuum fluctuations, Wheeler's quantum foam.
Quantum foam.
Yeah.
The idea that space-time itself is turbulent at the tiniest scales.
Right. At the Planck length, space-time might not be smooth, but a frothing sea of energy and geometry fluctuations. Those fluctuations could be the reverberations influencing the particle.
But you said Planck time scale. That makes it pretty speculative, right?
Yeah.
You can't exactly build a Planck time camera.
Yeah. Not even close. It puts these dynamics firmly in the realm of quantum gravity, which is still largely theoretical. It's definitely not directly testable with current tech.
Now, there's a big catch with these kinds of theories, isn't there? Something called Bell's theorem.
Ah,
Yeah.
yes, Bell's theorem. It's crucial. John Bell proved mathematically that if you want a theory that assumes realism, properties exist before measurement, and delocality, no faster than light influence.
Then that theory simply cannot reproduce all the predictions of quantum mechanics.
Correct. And experiments have overwhelmingly confirmed the quantum predictions, violating Bell's inequality.
So what does that mean for our oscillatory model, if it's realist?
It must be non-local. There's no way around it if it wants to match experimental results. Those reverberations in space-time have to somehow transmit influence instantaneously or faster than light across space.
So it has to embrace Einstein's spooky action at a distance.
It's forced to, yes. Any deterministic, realist completion of quantum mechanics has to grapple with non-locality. It's baked in by Bell's theorem.
Okay, so this non-local realism, it reminds me of another interpretation. De Broglie-Bohm theory or pilot waves?
Exactly. That's probably its closest conceptual cousin. The de Broglie-Bohm interpretation is the most developed example of a deterministic, realist, and explicitly non-local quantum theory.
How does that one work?
It posits two things: real particles that always have definite positions, and a real physical pilot wave, described by A, the wave function, that guides them. The wave function isn't about probability here. It's a physical field that literally steers the particles.
It's non-local too.
Oh yes, explicitly. The particle's velocity is determined by a guiding equation that depends on the pilot wave. And because the pilot wave can fill all of space, a particle's motion can instantaneously depend on the positions of all other particles in the universe via the wave.
Wow. How does it handle measurement?
No collapse needed. When a measurement happens, the pilot wave evolves, maybe splitting into different branches or packets. The particle, being guided, simply follows one path into one branch, making the other branches effectively empty.
And the randomness we see.
That comes from our ignorance of the particle's exact starting position within the initial wave packet. It's called the quantum equilibrium hypothesis. We assume particles start randomly distributed according to the wave function's intensity.
So comparing it to the oscillatory model.
The parallels are strong. The oscillatory model's infinite complexity or universal information sounds a lot like Bohm's universal pilot wave. And the reverberations in spacetime feel like an attempt to give a physical basis to Bohm's quantum potential, the mathematical term in the guiding equation that mediates the non-local influence.
Both are realist, deterministic, non-local.
Absolutely. The main difference seems to be how the particle moves. Bohm describes smooth, continuous trajectories guided by the wave. The oscillatory model suggests this rapid, Planck-scale jitter or oscillation.
So maybe the oscillatory model is trying to explain the mechanism behind Bohmian motion.
It could be seen that way, yeah. A specific hypothesis about the physical nature of the guiding influence and the particle's response.
What really strikes you about these approaches? Bohm, the oscillatory model, trying to solve these quantum puzzles.
It's their commitment to finding an objective, understandable reality behind the quantum math. They refuse to accept that the fuzziness or the measurement problem is the final word. They're looking for the gears underneath.
Trying to restore some classical intuition, maybe?
In a sense, yes. A reality that exists whether we look or not, even if it behaves in very non-classical, non-local ways.
Right. So let's dig a bit more into how this oscillatory model envisions those reverberations in space-time. What could they actually be?
Well, the model itself doesn't fully specify it, but it connects naturally to other ideas about universal background fluctuations.
Like what?
Like stochastic electrodynamics, or SED. This is a classical theory, surprisingly. It assumes that there's a real fluctuating electromagnetic field everywhere, the zero-point field, or ZPF. In SED, quantum effects emerge from classical matter interacting with this random ZPF. Things like atoms not collapsing are explained by energy absorbed from the field balancing energy radiated. Probability comes from the field's randomness.
Okay, so a random background field causing quantum effects.
Then there's stochastic quantum mechanics, SQM. This models particle motion as a kind of random walk, like Brownian motion, tiny random kicks. And interestingly, you can actually derive the Schrödinger equation from certain types of these random processes. SQM doesn't necessarily specify the source of the randomness, but SED provides a candidate, the ZPF.
And the quantum foam idea fits here too.
Definitely. Wheeler's concept of space-time itself fluctuating wildly at the Planck scale, that foaminess could be the source of the reverberations. Particles are constantly being jostled by space-time itself. Quantum gravity theories are trying to flesh this out.
So the oscillatory model borrows this idea of a fluctuating background.
Right. It takes the concept of a physical, energetic background, maybe electromagnetic, like SED, maybe gravitational, like quantum foam that permeates everything. The reverberations are the effects of this background.
But here's the twist, right? SED and SQM are usually stochastic random.
Exactly. That's the crucial difference and the unique synthesis the oscillatory model attempts. It takes the physical picture of a fluctuating field, but says the particle's response, its oscillation, is deterministic, not random. It's influenced by the field, but its motion follows definite laws based on that influence.
So it's like blending Bohm's determinism with the physical field ideas from stochastic theories.
That's a good way to put it. But the huge challenge, the mathematical mountain to climb, is showing that this deterministic oscillation, when averaged over time, precisely reproduces the probabilistic Born rule and the wave-like behavior of the Schrödinger equation.
You have to get the exact right statistics out.
You absolutely do. That's the make-or-break mathematical step. How does this deterministic jitter average out perfectly to match quantum statistics?
It is fascinating, though, how it tries to make things like non-locality less ghostly by grounding them in potential physical processes in spacetime.
It's an attempt to give substance to the spookiness, yeah.
And this idea of infinite complexity or universal information being everywhere, That connects to some even bigger, more abstract ideas in physics, doesn't it?
Oh, absolutely. It touches on some really profound concepts about information, reality, and interconnectedness.
Like what comes to mind?
Well, one framework is relational quantum mechanics, RQM, championed by Carlo Rovelli. RQM says a quantum system's state isn't an absolute property of the system itself. It's relational. It only exists relative to another system, an observer.
So properties only become real upon interaction.
Essentially, yes. A property is defined by the interaction between two systems. What we call collapse is just one system updating its information about another after they've interacted. The wave function in RQM isn't a real thing out there. It's a tool for predicting the relationships and interaction outcomes. It's about information.
Could you view the oscillatory model through that lens?
It's an interesting thought. Maybe the oscillation isn't a physical jittering in time, but represents the particle's potential to manifest different properties in relation to different possible interacting systems. The infinite complexity becomes the web of all potential relations.
That might sidestep the non-locality issue a bit.
It could potentially offer a different way to think about the interconnectedness without requiring faster-than-light physical signals in the same way. It shifts the focus to information and relations.
What else? Any other big ideas it connects to?
The holographic principle. This is mind-bending stuff from string theory and black hole physics.
Right, the idea that our 3D reality might be encoded on a 2D surface, like a hologram.
Exactly. It comes from studying black hole entropy, which scales with the whole surface area, not its volume. This hints that the information content of a region might be fully described by its boundary. If this principle applies to the whole universe, then our 3D experience could be a projection of information stored on some distant 2D cosmic horizon.
How does that connect to the oscillatory model's infinite complexity?
Well, if the universe is holographic, then information about the entire system is fundamentally encoded non-locally, potentially accessible at every point within the 3D projection. The infinite complexity could be this holographic information field, and the reverberations in space-time might be the physical way this underlying holographic code manifests locally, dictating the particle's oscillation or behavior.
So the particle's jitter is dictated by the global holographic pattern.
That's a possible, though highly speculative, connection. It provides a potential physical grounding for why information about the whole could be present at every part.
These ideas, RQM, holography, Bohm, the oscillatory model, they all seem to grapple with reality being fundamentally non-separable, right? Interconnected in some deep way.
That's a key theme, yes, quantum holism. The idea that the whole is more than the sum of its parts and that parts are defined by their relation to the whole. These interpretations are all trying to formalize that intuition in different ways.
Okay, so we've explored this oscillatory model quite a bit. Let's try to synthesize. What are its biggest strengths conceptually, and what are the major roadblocks?
Strengths first. I think the main appeal is its ontological intuition and realism. It gives back a picture, however strange, of particles having definite properties existing objectively. It tries to say what's really there.
It answers the what is it doing when I'm not looking question.
Right. Second, its potential resolution of the measurement problem. Measurement becomes straightforward, just observing a rapidly changing, definite state. No collapse, no parallel worlds needed. It's elegant in that way.
And the third?
The proposed physical mechanism. Even if speculative, trying to link quantum behavior to spacetime dynamics, vacuum energy, or quantum gravity. That's ambitious and potentially unifying. It aims for a deeper physical explanation.
Powerful ideas. But the challenges seem pretty huge, too.
They are significant, yes. First and foremost, non-locality and Bell's theorem. Keep coming back to this. To match experiments, it must allow faster-than-light influence. That clashes fundamentally with the spirit, if not the letter, of special relativity. How do you reconcile that?
That's a major hurdle. What else?
The biggest mathematical challenge is deriving the Schrödinger equation. The model postulates a new underlying dynamic, these deterministic oscillations. It has to show, rigorously, how the familiar wave-like evolution described by Schrödinger emerges as the time-averaged behavior of this deeper process.
That sounds incredibly difficult.
It is. You need to define the precise laws of the oscillation and the reverberations and prove they lead to the right quantum dynamics.
And similarly for probabilities.
Yes, deriving the Born rule. Why should the probability of finding the particle in a certain state be exactly the squared amplitude of the wave function? The deterministic oscillation must somehow naturally produce those precise statistics upon measurement time and time again. That's not trivial.
And finally, the mechanism itself.
But the physical nature of the reverberations, it's still quite vague. What is this field or influence? How is it described mathematically? What are its governing equations? How does it store or represent infinite complexity? How does it interact with particles specifically? Without formalizing this, it remains more of a conceptual sketch than a full theory.
So, summing up,
I'd say the oscillatory model is conceptually very rich, intellectually stimulating. It offers an intuitive, realist alternative that tackles major quantum paradoxes head-on. It's a fascinating synthesis of ideas from Bohmian mechanics and stochastic approaches. But currently, it's more like a philosophical framework or perhaps a research program proposal. To become a viable scientific theory, it needs to overcome those massive mathematical hurdles deriving Schrödinger and Born and provide a much more concrete, formalized description of its core mechanism, the reverberations, while also finding a way to live with non-locality.
it really highlights that even after a century, the quantum story isn't finished, is it? We have this incredibly powerful tool, but the quest for what it truly means about reality is wide open.
Absolutely. Bold ideas like this, even if incomplete, are crucial for pushing that understanding forward.
Okay, let's leave our listeners with something to chew on. Here's a final thought. If this model, or something like it, is right, if reality at its base is this incredibly fast, deterministic jitter, maybe driven by quantum foam, could our everyday perception of smooth, flowing, continuous time actually be an illusion, an emergent property, just the slow-motion average of these ultra-fast fundamental ticks? What would that imply about the real nature of time itself? Is it fundamentally granular, choppy, down at the Planck scale? Something to ponder. We hope this deep dive helped connect some quantum dots for you, maybe sparked a few aha moments. Thanks for diving deep with us.